Understanding sequences. A sequence is an ordered list of values, often representing quantities that change in discrete steps, such as drug levels after each dose or bacterial counts over time. The limit of a sequence describes its long-term behavior, revealing whether the biological process it models stabilizes, grows indefinitely, or oscillates. A converging sequence approaches a fixed value, modeling stabilization, for example, reaching a steady-state drug concentration. A diverging sequence increases without bound, modeling uncontrolled biological growth such as tumor expansion or unchecked viral replication. Recursive definitions are common in biology and often require limits to determine equilibrium or steady-state conditions. Limits at infinity. Limits as x approaches infinity, or negative infinity, examine how a function behaves as the input becomes very large. This concept is crucial for understanding the long-term outcomes of biological processes. In monokinetics, microbial growth saturates at a carrying capacity K, even if resources remain abundant. Horizontal asymptotes, found using limits at infinity, help predict carrying capacities in ecological and microbiological models. Growth versus decay comparisons rely on limits to determine which effect dominates over time. In epidemic modeling, exponential growth often outpaces polynomial terms, emphasizing the power of exponential spread. Limits at finite points. These limits evaluate what a function approaches as x approaches a specific value, for example, as x approaches a value c, even if the function is undefined at c. One-sided limits explore behavior as x approaches from the left or right. They are essential for modeling threshold effects, such as the activation point of a drug or a sudden physiological response. If a limit equals infinity near a specific point, it models unbounded change, like a sudden spike in ion concentration or a crash in pH. Discontinuities in models often reflect biological reality, but they require limit analysis to assess whether the model remains realistic. For instance, a piecewise function modeling bacterial growth at different temperatures must be evaluated using both one-sided limits at the boundary. Continuity. A function is continuous at x equals c if all three conditions are met. Fc is defined. Lim of fx as x approaches c exists. Lim of fx as x approaches c is equal to fc. For functions with left and right limits, both must agree for the overall limit to exist. Continuity ensures that small input changes produce small output changes, which is vital in modeling enzyme kinetics and dose-response relationships. Discontinuities, for example, jump discontinuities, can be biologically meaningful, representing threshold responses or rapid biological shifts. The intermediate value theorem, a consequence of continuity, is frequently used in biology to demonstrate that a system must pass through a certain state. Algebraic and graphical tools. Limit laws help simplify complex biological functions during analysis. The squeeze theorem is useful when exact values are hard to determine but bounding behaviors are known. Graphical analysis offers visual insight into biological systems, indicating saturation, divergence, or threshold behavior. Numerical approximation of limits from data bridges the gap between theoretical models and real-world measurements, especially when explicit functions are unavailable. Biological applications. 1. Viral infection dynamics. Early infection stages typically show rapid viral load increase. Limits model what happens as time progresses indefinitely. Untreated models assess potential explosive viral growth, while treated models include decay components, predicting how quickly the virus may drop to undetectable levels. These insights shape treatment timelines and public health strategies. 2. Drug dose accumulation. Repeated drug doses create a sequence of concentrations over time. Under the right conditions, this sequence converges to a steady state level, crucial in pharmacokinetics. Misjudging this limit can lead to underdosing, ineffective treatment, or overdosing, also known as drug toxicity. Geometric or arithmetic recursive models often describe this accumulation, with long-term behavior guiding dose scheduling. 3. Pathogen growth and the Monod model. The Monod equation relates microbial growth to nutrient concentration. As substrate availability increases, growth levels off, modeling biological saturation. Limits help determine whether additional resources meaningfully increase growth or are wasted input. This model is especially important in chemostat design and wastewater microbiology. 4. Threshold behavior in enzymes and hormones. Many biological functions exhibit threshold behavior, changing dramatically past a certain point. For example, insulin secretion might remain minimal until glucose exceeds a threshold, after which response surges. One-sided limits help model and analyze such behavior. These functions are often piecewise defined, requiring careful analysis at boundary points. 5. Tumor growth and limiting behavior. Tumor growth often shows an initial exponential phase, followed by a plateau due to nutrient or spatial limitations. Limits as time goes to infinity estimate maximum tumor size, which informs prognosis and treatment planning. Some models balance exponential growth with inhibition, and limit behavior helps predict treatment outcomes or remission potential. Common mistakes to avoid. Confusing limit existence with limit value. A function approaching infinity does not mean the limit exists in the strict mathematical sense. Vertical asymptotes signal unbounded growth, not a defined limit. Plugging into undefined points. Avoid direct substitution into functions that are undefined at a point. Always simplify the expression and check the domain before substituting. Watch for holes in graphs. These require limit evaluation, not plug-in, ignoring one-sided limits. Especially in piecewise functions, both left and right limits must be analyzed. If they don't agree, the overall limit does not exist. This is crucial for modeling stepwise or threshold effects. Misapplying algebraic rules. Limit laws only apply if the limit exists from both sides. Misuse can lead to invalid simplifications and wrong conclusions. Always factor, reduce, and check for discontinuities before applying limit laws. Misreading graphs. Don't confuse removable discontinuities with vertical asymptotes. Misinterpreting graphs can result in biologically invalid conclusions. Know the difference between holes, jumps, and asymptotic behavior.